So first of all, I'd like to thank the organizers for inviting me to give this colloquium. And so I'll be telling you about my recent observation here at the Technion of quantum Hawking radiation and its entanglement in an analog black hole. And this is the world's first observation of Hawking radiation in any system. And this work builds upon a rich theoretical history, starting with Bekenstein from the Hebrew University, who said that he invented the field of black hole thermodynamics. He said a black hole should have both entropy and temperature. Hawking then said the black hole should emit radiation at the very temperature predicted by Bekenstein. And in making this prediction, Hawking combined general relativity with quantum field theory. And this is considered important because one would like to discover the theories of quantum gravity. And this is a first step, treating the gravity classically using general relativity and combining that with the quantum field theory. The problem with confirming Hawking's calculation is that the Hawking radiation from a real black hole should be exceedingly weak, because the temperature, the effective temperature of the Hawking radiation from, say, a black hole of a few solar masses is less than a microkelvin, and that's completely dominated by the other sources of radiation, such as the cosmic background radiation. But perhaps perhaps one can observe the Hawking radiation from very small black holes, because a smaller black hole has a higher Hawking temperature. So maybe there are primordial black holes which can be discovered, or perhaps at the LHC, perhaps black holes will be produced. But in 1981, Bill Unruh came up with the idea that one can create an artificial black hole in the laboratory, where sound plays the role of light, and try to confirm Hawking's calculation in that way. And in his paper, he wrote, "Black hole evaporation is one of the most surprising discoveries of the past 10 years." So apparently, verifying this calculation was his motivation for proposing analog black holes. Now, the medium in which one can make this analog black hole could be, for example, a Bose-Einstein condensate, or superfluid helium-3, or an electromagnetic waveguide, ultra-cold fermions, rings of trapped ions. There have been many systems proposed. Slow light in an atomic vapor was considered for a while, but then it was found that it wouldn't actually work. Light in a nonlinear liquid is a possibility, or exciton-polariton condensates. Furthermore, the black hole could have two horizons. In 2014, I did an experiment, which I gave a talk about where the black hole had two horizons. In that case, the two horizons act like a laser cavity for the Hawking radiation, and the Hawking radiation generates additional Hawking radiation in a stimulated sort of way. So that's called the black hole laser. And furthermore, the black hole laser could be in a ring configuration. On the experimental side, my group has been studying this problem, and only this problem, since 2009. And the research has been systematic, starting with learning how to create an analog black hole, and then learning how to create and observe a small number of phonons in the analog black hole, since the Hawking radiation is phonons. Then we actually saw the phonons in the Bose-Einstein condensate, which is just due to the finite temperature of the condensate. Then finally, combining the phonon work with the sonic black hole, we were able to see the self-amplifying Hawking radiation. That's the lasing Hawking radiation with the two horizons. And now I report the observation of the quantum Hawking radiation, which is spontaneous, and its entanglement. So another area under being studied currently is water. This is a classical system, and with the surface waves on the water, one can, in some sense, simulate black holes. Particularly more white holes are simulated rather than black holes. Maybe I can explain to people who want to know what a white hole is, but sort of the inverse of a black hole. And so and recently some noise correlated, the white hole was seen to radiate some sort of noise which is stimulated by the fluctuations in the water. Furthermore, nonlinear optical fibers are currently an active area of study. People are trying to see the Hawking radiation in nonlinear optical fibers, as well as in exciton-polariton condensates. On the theoretical side, entanglement has been a recent area of interest. And last year I wrote a paper describing how one could actually measure the entanglement of the pairs created in Hawking radiation, and I implemented the method here. Now I'd like to discuss some of the fundamental issues surrounding black holes, because when we look at the analog black hole, we'll want to see what we could learn about real black holes. So these are issues of black holes which are not related to the black hole itself. In other words, a black hole is a sort of a testing ground for laws of physics which have far-reaching implications far beyond black holes themselves. Okay, for example, there's this idea of Planck scale physics, the physics on length scales, very, very short length scales. There's what's called the information paradox, which we'll discuss that in a moment. Then there's the idea of quantum gravity. So firstly, Planck scale physics. That's supposed to be a circle. Okay, anyway, this is a real black hole, and this is the event horizon of the black hole. And the Hawking radiation is emitted from the event horizon. And as the Hawking radiation moves away from the black hole, it gets redshifted. So if we trace the Hawking radiation back to the moment that it was created at the event horizon, then the wavelength should be infinitesimally small. And it'll be so small that it'll even be on the Planck length scale. And the laws of physics on the Planck length scale are not known. So it was thought that perhaps the Hawking radiation somehow tells us, since it's emitted at the horizon, it somehow tells us something about the Planck length scale. Another issue is the information paradox. So the information paradox was presented by Stephen Hawking soon after he predicted Hawking radiation. And he said, well, he didn't say it in exactly these words, but information which crosses the event horizon is irretrievable. Because the Hawking radiation which is emitted is random. So information enters the black hole and then later is emitted as Hawking radiation, but it's emitted with no information. So the information is lost. And thus, Hawking concludes, there's uncertainty beyond the Heisenberg uncertainty principle. And this violates quantum mechanics. So we see this conflict between general relativity, which predicts black holes, and quantum mechanics. So this is the information paradox. Now, we can really see the information paradox even more clearly if we realize that due to the Hawking radiation, the black hole evaporates. So with time, the black hole is going to shrink away. And so perhaps maybe one thinks the information that one throws into a black hole is somehow stored inside the black hole. But eventually, the black hole is going to vanish due to the emission of the Hawking radiation. So where did the information go? So one possible solution to the information paradox, and there are many proposed solutions to the information paradox. One possible solution is that the Hawking radiation carries the information, that the Hawking radiation emitted at early times is entangled with the Hawking radiation at later times, and the information is inside of this outgoing Hawking radiation. And this falls into the category of quantum gravity, since the general relativity doesn't predict this entanglement here. So this goes into the field where into the idea where the background, the curved space-time is quantized rather than being just a classical smooth background. So, but there's a problem with this solution to the information paradox in that the Hawking radiation, outgoing Hawking radiation, is entangled with the partner particles. Hawking radiation is the production of pairs. One particle comes out of the black hole, and another particle falls into the black hole, and this pair should be entangled, even maximally entangled. So that means if the Hawking radiation is already entangled with a partner, it cannot be entangled with the earlier Hawking radiation. So in other words, the entanglement here makes this solution impossible, you could say. One solution to this problem of disentanglement is what's called the firewall. The firewall is the idea recently proposed, that controversial idea, that the event horizon has a firewall which breaks the entanglement between the partners and the Hawking radiation. In other words, the entanglement is broken, and that releases a lot of energy. So there's incredible amounts of energy here at the horizon of a black hole. Another possibility recently proposed by Hawking and company is proposed this year is the idea of soft hair, that the black hole has degrees of freedom, soft hair on the surface, on the event horizon, and these are zero energy particles, but they can carry the information. And this also falls under the field of quantum gravity. So now, how can analog gravity help with all of this? So analog gravity, in the work that I'll be describing today, we can confirm two elements in this discussion. Firstly, that Hawking radiation occurs at all. So as you've seen, Hawking radiation is definitely an important element in the discussion of all these issues. So we'll see that Hawking radiation indeed occurs. Also, we'll even see that the Hawking and partner particles are indeed entangled, pointing out that one really does need some solution to this information paradox. So in general, the field of analog gravity, how does it provide input to real gravity? I'm interested in studying analog gravity to learn something about real gravity and real black holes. So here are the achievements to date. First of all, there's a theoretical result that Hawking radiation is in fact not sensitive to Planck scale physics. One does not learn about these ultra-short length scales by studying Hawking radiation. Another achievement is that a white hole horizon, this was in water, was seen to mix modes, mixing those pairs, mixing the modes of the pairs. And then in our stimulated Hawking radiation experiment with two horizons, we saw that Hawking radiation actually occurs. And then today, I'll discuss the verification of the spontaneous Hawking radiation, the quantum Hawking radiation, as well as measuring the entanglement between the Hawking and partner particles. Another recent result was the stimulated emission of radiation by a white hole due to, as I mentioned, the fluctuations in the water. Some goals that one can find in the literature of analog gravity is observing superradiant scattering from rotating black hole analogs, and simulating cosmological particle creation, and simulating wormholes. So now, getting down to the physics of Hawking radiation. This is a real black hole. The Hawking radiation is a pair. So here's one particle which exits the black hole. This is, say, a photon, and it has positive frequency and therefore positive energy. This is like the usual photons that we're used to in our day-to-day lives. Now, however, the partner which falls into the black hole has, while it's directed towards the horizon, it can never reach the horizon, and it has negative energy and negative frequency. So one can have a pair with zero total energy. So one can produce these pairs with no input, no source of energy. It can happen just spontaneously. And so this is the Hawking radiation, and Hawking predicted a thermal distribution of pairs, that one doesn't just get one specific frequency, one gets a thermal distribution. And the bigger the black hole, the lower the temperature of this thermal distribution. Now here's the analog black hole, which I'll be discussing today. The black hole will radiate wavelengths which are on the scale of the black hole or longer. It won't emit shorter wavelengths than the scale of the black hole. So that gives an effective temperature, the diameter of the black hole. And then the black hole could be in thermal equilibrium with something if it radiates and something shines on it. Conceivably, although it seems difficult that it could actually reach equilibrium if one thinks about the time scales involved. But anyway. Okay, so here's the analog black hole. So this is a Bose-Einstein condensate with about 4,000 atoms. And it's a tube-shaped condensate. And it's flowing from left to right. So in this region, this flow is subsonic. And here, and past this point, the flow is supersonic. So if we consider a phonon on the subsonic side, it can go forward against the flow in the laboratory frame. And this phonon has positive energy and positive frequency. However, a phonon directed against the flow on the supersonic side is swept backwards by the flow. It doesn't actually go forward. And this phonon has negative energy and negative frequency, and it can never reach this point which we'll call the analog of the horizon. So this is analogous to a photon trying inside of a black hole. So one can have a pair of these phonons with zero total energy. So I'd like to take a moment more to discuss what negative energies are, just to give some simple examples of negative energy. So here are a couple of examples. Here's a system of particles all moving at the same velocity. If one of the particles will stop moving, like this one, that's an excitation with negative energy. The energy of the system goes down. Another example would be a Doppler shift. Let's say we have a wave with some frequency omega in one reference frame, and then there's some other reference frame which is moving very fast enough that the frequency in this other reference frame becomes negative. And that would also be an example of a negative energy. Phonons, or this Doppler shift is another example. And that's the relevant case for this system. This wave in the laboratory frame is Doppler shifted so much that it has negative frequency and the phonon has negative energy. So we want these pairs to be stimulated by vacuum fluctuations, so to be analogous with Hawking radiation. So what are vacuum fluctuations in this system, in this Bose-Einstein condensate? Well, here's a picture of a BEC with phonons. This picture comes from one of our works where we were working up to observing Hawking radiation, and we learned how to create and observe small numbers of phonons. So here are some phonons which we've created in the BEC, and that means that this is not vacuum, because when we say vacuum in this context, we mean no phonons. It's the phonon vacuum that we're discussing. So here's a BEC with phonons, not vacuum. Here's a BEC with no phonons, which is then vacuum. So you could say, well, okay, in this image, the BEC has some smooth macroscopic wave function. So where are the vacuum fluctuations? Well, if we look closely at the BEC, we see that it's actually composed of point-like atoms. And on top of one of these atoms, the density is essentially infinite, and in between the atoms, the density is 0. And these are the vacuum fluctuations. This is true even if there are no phonons in the BEC. And then, of course, for every realization of the experiment, these point-like atoms have a different configuration. So we'll observe the creation of the pairs with positive and negative energy stimulated by the quantum vacuum fluctuations. Now, how does one actually observe the Hawking radiation? One is looking for some very small fluctuations on this background. And one would like to see, it's been proposed that one can use the correlation function. So let's say pairs are emitted here from the horizon, and one phonon goes this way, and one phonon goes this way. And so one could look at a point, x and x prime, which are equal propagation times from the horizon, and these two points should be correlated. And it doesn't matter if the points are far apart or close together, as long as they're equal propagation times from the horizon. So here, if we plot the correlation function versus x and x prime, there's a line of points here, and each point along this line is a pair of points which is equal propagation times from the horizon. So one's looking for this feature in the correlation function. Those are all the pairs of points which are equal propagation times. What I explained in this theoretical paper is that we can use this very same correlation function to see that the pairs are entangled. So what one does is, since this is a position space observation of Hawking radiation, one can compute the Fourier transform and make a k-space observation of the Hawking radiation. So how does that work? First, we take the cross-section of this correlation function, which looks like this. This is the cross-section of this feature. And then one computes its Fourier transform of this cross-section, and one can show that that gives us this product of operators. These are the correlations between a Hawking particle with wave number k and a partner particle with wave number kp. This is KHR and kp. So once one has these correlations, one can then plug it into this what's called the non-separability criterion. This implies that if the correlations are large compared to the populations, these are the populations of the Hawking and partner particles, then the state must be non-separable. So now we have this criterion, and we can, by taking the Fourier transform of this cross-section of this feature, we get these correlations. We see if the correlations are large compared to the populations, and if so, so that delta is a negative number, then the state is non-separable or entangled. So there's been an assumption made here. In getting this pair of operators, we've thrown away these three pairs of operators. And why can we throw them away? We can neglect them because these are correlations between waves of different frequencies. Meaning, here's a partner particle which has the same absolute value of frequency as this Hawking radiation particle. However, due to the Doppler shift, a wave going in the other direction has a different frequency than the wave going this way, because this is a flowing condensate. So that means that this wave going the wrong way has a different frequency from the partner particle. And so we're neglecting the correlations here. For example, this term is correlations between this wave and this wave. And so I can't think of anything in this system which would correlate at widely spaced waves with different frequencies, we can safely neglect these correlations. Hawking radiation certainly wouldn't correlate these two waves. So this method of measuring entanglement is valid in an inhomogeneous flowing condensate. This is not a general method for measuring entanglement. Furthermore, one would usually like to measure entanglement by measuring non-commuting observables. Sometimes there's been a new paper proposed explaining how to measure entanglement without measuring non-commuting observables. But usually one measures non-commuting observables. And in this case, the non-commuting observables are these correlations which don't commute with the populations. So now I'll skip this part just to save time, but one can show that this method of measuring entanglement using this delta criterion gives exactly what one would expect when one considers the linear dispersion relation, which is in strict analogy with a real black hole. One gets maximal entanglement. So now the experimental technique. So how do we accelerate this condensate to supersonic speeds? Well, we found that a great way to do it is by making a waterfall potential. So this is the potential, and one has the Bose-Einstein condensate flow over the potential and gets accelerated to supersonic speeds. So how do we create this potential? This is a laser beam, which is coming out, an elliptical-shaped laser beam, which is coming out of the board, coming out at us, and it's been cut in half by a knife edge and then imaged onto the condensate with high-resolution optics. And so this forms a potential step for the atoms because the blue laser beam is creates a repulsive potential for the atoms. And then this blue laser beam is moved at a constant speed by means of a high-resolution acousto-optic modulator, for those who work with optics. And one needs a high-resolution acousto-optic modulator to maintain this very sharp edge while still moving the beam. And the reason that the blue light is used is to make the sharpest edge possible. So it's useful to look in the reference frame where the beam is not moving and the condensate is moving to the right. So the condensate is flowing in here, in this region, and then reaches the step and gets accelerated to supersonic speeds. we'll see that in a minute. On this side, it's about 0.5 millimeters per second, and then even less over here. We'll see the numbers in just a moment. So, in addition to this laser beam, there's also imaging of the condensate, also with high-resolution optics, and this is phase contrast imaging, which means that we see the phase shift of the laser beam as it goes through the atoms. And the signal is very weak. The reason I use this type of imaging, this is sort of I modified the usual type of phase contrast imaging, is to get as much signal as I possibly could, because there's only about 4,000 atoms in this cloud, and that gives one very few photons to work with. The pulse has to be short to not perturb the cloud during the pulse. So there's very few photons available, and so I want to get as much signal as I could. I use phase contrast imaging, which is very close to resonance, actually, to maximize the signal. And, okay, then furthermore, there's also a trapping laser beam at 812 nanometers. This is a laser beam, a red-detuned laser beam, so it creates an attractive potential for the atoms. And one would like, for this beam is very weak because I wanted low density. So this beam is not strong enough to support the atoms against gravity. So there's a magnetic field gradient which counteracts gravity. And this whole system, since the Hawking radiation is a very weak effect, so one needs to repeat the experiment many, many times, even though I've used as much signal, extracted as much signal as I could, I still needed to repeat the experiment many, many times, 4,600 times, which corresponds to 6 continuous days of measurement. So the system has to remain very stable for 6 days, meaning because this laser beam is very weak, any slight change in the angle of the beam will cause the condensate to tilt and flow to the left or flow to the right. So for example, the optical table must be extremely stable. It's the angle of the optical table for 6 days. And so that required special types of air support. And so now also for another issue is heating. This condensate is very cold. We developed a technique to measure the very, very low temperatures involved here. It has to be very cold so one can see the Hawking radiation, which is a very low temperature radiation. So the condensate is less than 1 nanokelvin in temperature. So any motion of this beam, if this beam, say, shakes around a little bit, that will easily heat the condensate more than above 1 nanokelvin. So this, in order to make all these laser beams have to be very stable, so they're all shielded against motion of air in the room. So here are some numbers. The speed of sound outside here is 0.57 millimeters per second, and the flow velocity is 0.24 millimeters per second. These numbers are determined from a measurement of the dispersion relation that I'll discuss soon. Furthermore, inside the black hole, the speed of sound is 0.25 millimeters per second, and the flow velocity is 1.02 millimeters per second. So this is very much supersonic flow inside the black hole. Furthermore, one can see that this is a 1D system because the trapping frequency in the perpendicular direction is 140 hertz, whereas the interaction energy is 70 hertz. So the radial degree of freedom is frozen out. Now here is the integrated profile of the density here. And here's the region where we're going to see Hawking radiation, and here's the region where we're going to see the partner particles. If one zooms in on the horizon here, one sees that the width of the horizon is a few healing lengths in width. The healing length is the length associated with the interaction energy of the condensate. So it's a few healing lengths in width, a few healing lengths in width, implying that the system is basically hydrodynamic. And it's consistent with a measurement, with the prediction, this green curve, which is the prediction of this theoretical paper, which says that it should be like half a gray soliton. The shape, the density profile should be half a gray soliton. And it is similar to half a gray soliton. And one can also show here, if one would like to, that this system has phase coherence even though it's 1D. One can say a 1D system should not have infinite phase coherence. but it has very, very long phase coherence. One can show that. So now we're going to perform two different types of experiments. One experiment for measuring Hawking radiation, the horizon is going to move, this potential is going to move at a constant speed. As shown in this graph, as a function of time, the position moves constant speed like this black curve. The preliminary experiment, we cause the horizon to oscillate. In other words, instead of moving at a constant speed, it oscillates sinusoidally, like the green curve, with a 1 micron amplitude, and we can apply any frequency we want. So in other words, we make the horizon oscillate, and this generates waves. We generate a wave coming out of the black hole and a wave falling into the black hole, and we can see what the modes are of this system, and then see if it's consistent with the Hawking radiation which we observe. So here's the oscillating horizon experiment, the preliminary experiment. Here's the correlation function, which is obtained. And this quadrant of the correlation function is the correlations between points outside and inside the black hole. And one sees this wave pattern here, showing that there are these correlated waves, one going this way and one going this way. And we can compute the Fourier transform of this wave pattern and get the wave number of the waves created. And we can trace out the dispersion relation, because we've applied a frequency and we observe the wave number. So here's the dispersion relation outside the black hole. Here's the dispersion relation inside the black hole. And here are the partner particles, the ones with negative energy, or the negative norm modes, as they're called. And we could see that there's some, because of dispersion, the dispersion relation is not really linear. There's some maximal frequency for the outgoing waves, because these waves have a dispersion relation pointing to the right, meaning the slope is positive. They're moving into the black hole. That positive dispersion relation, positive slope, ends at some point. So there's a maximum frequency and a corresponding maximum wave number. And we'll see in the Hawking radiation experiment that the maximum wave number of the Hawking radiation agrees well with the maximum wave number seen in this preliminary experiment. Furthermore, this oscillating horizon experiment produces, one would expect it'll produce in some sense the same spectrum, meaning the horizon has a certain sharpness. So there are certain wavelengths that can be produced by this the sharpness of the horizon and no more. And it's the same horizon producing the Hawking radiation as producing these waves that we've generated. So we expect the same spectrum in some sense. So here is the rate at which the particles are produced. The dashed curve is what we would expect from the Hawking radiation experiment, which we'll discuss in a moment. And the solid curve is what we actually see in this experiment. And so we see that there's good agreement here. So everything is consistent. Furthermore, the angle of this feature is similar to the angle that we're going to see in the Hawking radiation experiment, implying that the phase velocities have the same ratio in the two experiments. So now getting to the main experiment, the Hawking radiation experiment, where we move the horizon at a constant speed and look for the Hawking radiation. And the resulting correlation function looks like this. So we can see here in the correlations between the inside and outside the black hole, this gray band extending from the origin, from the horizon. And this is the observation of the Hawking radiation. These are the correlations between the Hawking and partner particles. And this is, as I mentioned, obtained from the entire ensemble of 4,600 images. We can see, we could take the profile of this feature, which looks like this. And we see that this profile has some finite area. It's not like the oscillating horizon experiment. We had that sinusoidal pattern. Here we have just some finite area implying some K distribution, some thermal-like K distribution. And one could show that the fact that the area is finite implies that the population is going like 1 over omega for very small omega. So it's thermal for very long wavelengths, very low energies. So at this certain angle, there's this minimum. If we integrate along parallel lines parallel to this angle, one sees this profile. So this is the profile of this feature. Now, one can compare with simulation, numerical simulation. In a numerical simulation, one sees a similar feature there. one also sees a similar profile. And in this simulation, due to the way that the fluctuations were added to the simulation, one ends up with these fringes, which are just an artifact of the simulation. Furthermore, the fluctuations here were added to the simulation well after the formation of the horizon, showing that this Hawking radiation seen is a stationary effect. We can measure the population by this technique that we developed to measure these very small populations. That's how we can measure these low temperatures. We measure a temperature here of 0.1 of the chemical potential of the condensate. Whereas before this work, it was written in the literature that the lower limit for the temperature of a condensate is thought to be around the chemical potential. And we measured 0.1 of the chemical potential as the temperature. So by applying this technique of measuring phonons to this region where we see the Hawking radiation, where we saw the Hawking radiation in the correlation feature, we get the following power spectrum. This power spectrum is proportional, as we explained in our paper, to the population plus the quantum fluctuations. So, the first thing one notices about this power spectrum of the noise is that it slopes downward as k goes smaller. So this is a sign of that quantum fluctuations dominate, because thermal fluctuations, as the energy goes lower, one gets more and more thermal fluctuations. So, and this zero curve is the pure quantum fluctuations corresponding to zero temperature. The difference between the measurement and the zero curve gives the population. And so here's the measured population. And this it agrees well with the Planck distribution, which is the dashed curve. And this gives us a measured Hawking temperature of 0.36 mc squared, or 1.2 nanokelvin. So that's the measured Hawking temperature. We can now measure the entanglement. We just need to get this second term. We have the population. We then take the Fourier transform of this profile, and that gives us the correlations. And so the Fourier transform squared of this profile. So the Fourier transform squared of this profile looks like this. Here it is, the solid curve. And we can see that the solid curve is well above the dashed curve as a function of k. The dashed curve is the populations. So we see entanglement for a wide range of k's. And in that preliminary experiment, where you remember where we generated the waves, then one sees that the solid curve is below the dashed curve. There's no entanglement, of course, when we generate the waves in that classically. So and we could see that this curve ends at the correct k value, which was from the preliminary experiment. This is the difference between the solid curve and the dashed curve, showing the entanglement over a broad region of k. And this curve qualitatively agrees with a numerical simulation. Furthermore, the solid curve is consistent with this light gray curve. This light gray curve is the Heisenberg limit. The correlations between the waves are limited by the Heisenberg uncertainty principle. They can't be too large. And so this agreement with the Heisenberg limit tells us two things. First of all, it tells us that the fluctuations are approximately thermal in this region, because the Heisenberg limit was computed by the thermal distribution. Second of all, it shows us maximal entanglement here. These are in agreement with the Heisenberg limit means maximal entanglement, but below this k value in this region, we're well below this gray curve, so we have less than maximal entanglement in this for lower energies. So we can ask, how statistically robust is the entanglement that we see? So we could look at it in two different ways. First, we could say maybe this 1.2 nanokelvin temperature that we measured is really incorrect due to some statistical variation or something, and it was really 2.7 nanokelvin. So now the solid curve is no longer above this dotted curve, 2.7 nanokelvin. But we could see that the 2.7 nanokelvin is completely ruled out by our measured power spectrum here. So that's not a significant possibility. Another possibility would be that this wide profile is actually much narrower, let's say. Say this black curve is actually on the left side of the dotted curve. It would have to be narrower by 90%. Well, that implies, since this is the Fourier transform of the profile of this feature, that would imply this feature is actually very wide. So although this feature looks like a narrow line, maybe it's actually a very wide line. But here's the profile of the feature. With the error bars, the width is determined plus or minus 16%, so 90% is ruled out by many sigma. Okay, so we found that it's statistically significant, that this curve is above the dash curve. We showed in a couple ways that it's statistically significant. So in conclusion, quantum Hawking radiation has been observed. The Hawking radiation is observed through the correlations between the Hawking and partner particles. The quantum nature of the Hawking radiation is verified by observing the entanglement. The experiment is well within the quantum regime, characterized by spontaneous emission and entanglement, since the 1.2 nanokelvin measured Hawking temperature is significantly less than 2.7 nanokelvin. The measurement shows maximal entanglement at high energies and no entanglement at the lowest energies. 1 over omega thermal behavior is seen at very low energies due to the finite cross-section of the correlation feature, and Planckian thermal behavior is seen at high energies due to the agreement with the Heisenberg limit. The oscillating horizon experiment, the preliminary experiment, agrees with the measurement in that it agrees with the Hawking temperature with the rate that the frequency response of the horizon, you can say. Furthermore, it agrees with the ratio of the phase velocities. That was the angle of the feature in the correlation function. We're in agreement. The width of the feature also was in agreement with the maximum K that we saw in the preliminary and the experiment with a Hawking radiation experiment. By the simulation, we verified the approximately stationary background on which the Hawking radiation occurs, as well as, again, the maximum K, giving the width of the Hawking partner correlation feature. So what are the implications here for real gravity? What did we learn about real gravity from these measurements? Firstly, black hole thermodynamics is verified experimentally, at least within the analog case, since we see that a black hole does radiate, and that confirms Hawking's calculation. Secondly, we saw that the Hawking partner pairs are entangled. And this confirms an important element in the discussion of information loss, because as we discussed at the beginning, this entanglement limits the amount of outgoing information that one can have in the outgoing Hawking radiation. Thank you.